And so what I want to do today is I want to pick up where we left off last class. And that was starting to talk about these advanced rules for probability. Um, so if you don't have this this PowerPoint printed out to take notes, you should still follow along. And you're going to notice that, as I was saying last time, that most of the slides you can see over here are blank anyway. So there's going to be a lot of writing and examples today. I have posted in the classroom. If you go into the classroom and then you click the homeworks tab, I have posted homework number 3. So that's not due for a while. That's not due till Tuesday the 16th, and that'll be the day of our next exam. If you look in the syllabus here, the 16th is our next exam. But if you download the homework, you're actually going to be, after today's class, be able to complete problems 1, 2, 3, 4, and 5. And then next week we'll handle the rest of them. But you should be able to complete problems 1 through 5. So I highly encourage you over the weekend to take a look at this homework and give the first few problems a shot. And then what I'll do on class on Tuesday next week is, if anybody has any questions on the homework, I'd be happy to go over some of the problems with you. So definitely just take a look at it this weekend. Okay. But it's not due till the 16th. So you got a while. You got a couple weeks. You got 2.5 weeks or something for it. All right. Otherwise, before I get started, does anybody have any questions about any of that or anything in general? All right. Take out have your calculator handy a little bit. We're going to use it not initially, but a little bit later on in class. And then one thing I do like to say is the first part of class tends to be a little dry. The first 40 minutes to an hour of class, just because a lot of it is like, here's a theorem, and then here's a real simple example with coins or dice. And then during the second part of class, I think we get to work some more interesting problems. So I always like to let you guys know when the lecture is going to be a little dry. So just hang on to that or remember that, okay? All right, one problem I do want to go back to. Let me just. Do you guys remember on Tuesday? I did this example where I said, suppose you flip a coin and then roll a die and you record your results. Do you guys remember this example that we did right here? A little bit. I got one yep. The thing that I want you to note here for today's lecture is just to recall the answers to these two questions, okay? Because what I'm going to do is I'm going to introduce some formulas in class, and I'm going to prove that they work by actually getting the same answers that we see here. So one of the questions we had was, what is the probability you flip heads or roll a 6? Okay. And what did we say that answer was? If you look on the screen here, what is the answer to flip heads or roll a 6 here? Yeah, thanks, Melissa. Yeah, it's 7/12, so you can see it right there. And then the next question I asked was, what was the probability of flipping heads and rolling a 6? All right, what did we say? Looking on the screen here, what's the answer to that one? Yeah. Yep. Thank you. Okay. And so just keep these in the back of your mind, because we're going to rework these problems a little bit differently than we did with the sample space and stuff. So just hang on to them. All right. So then we ended class last time using the complement rule. So we worked 2 examples of that, it looks like. And now I want to get through a couple more rules. All right. And the first one that we're going to talk about today is called the general addition rule. And it goes like this. For any 2 events, Okay, and we'll call those events E and F. Okay, so remember, events are subsets of a sample space in a probability experiment. So, when I show you the events in a little bit, this will ring a bell to you. So, but for any two events, E and F, we have the following. If I say, what is the probability that event E or event F happens? Okay. So look here. Let me go back to the slide real quick. Okay. If you guys remember when we worked this example, I said, what was the weird word here? And it was the word or. It was like, how do you tackle that? The word or in a probability statement. So whenever you have two events, if I'm asking you the probability of E or F happening, here's the thing. Whenever you see an or statement, you're always going to think this mathematical operator, addition. So you're going to take the probability of the first event and you're going to add to it the probability of the second event. Now, here's the thing. It's always addition. And then this is where it gets a little weird. Sometimes subtraction as well. So you're going to always add the probability of E plus probability of F, but sometimes you're going to have to take away the probability that events E and F happen. Okay. So now here's the thing. If the events E and F are disjoint, okay, so what disjoint means in probability is that the events are mutually exclusive, okay? What that means when I say events are mutually exclusive, it means they cannot happen at the same time, okay? So cannot happen at the same time. So if the events E and F are disjoint, cannot happen at the same time, can anybody tell me what they think then the probability that both E and F occur is equal to? If they can't happen at the same time, what do you think the probability they both happen is then? Anybody got a guess?
One.
No, you're close. What would be the other extreme? Yeah.
0.
Yeah, it's got to be zeros, right? So if the events are disjoint, meaning they cannot happen at the same time, then the probability that they both happen would be 0. Okay. So it's a little confusing. Okay. So sometimes you have to do subtraction, sometimes you don't. So what I want to do is I want to work one example to just show you that this formula definitely works. Okay. And then I'm going to show you an example of where you have events that are disjoint and events that are not disjoint, and why sometimes you need to subtract and sometimes you don't. All right. Is everybody everybody copy the formula? Everybody okay if I go to the next slide? Hold up. I'll hold up. Ugh. Let me know when I can go on, Michael. Okay. So here's the first example I do. I want to go back and work that coin flip die rule. So suppose you flip a coin. Let me go back. Was it? Did I do it the other way? Yep. Flip a coin and then roll a die. Flip a coin and then roll a die. Okay. You record your result. So the first question is, what's the probability and the question was, going back, look, you flip heads or roll a 6. You flip heads or roll a 6. Okay. So look, I'm going to write this as the following. It's the probability you flip heads or roll a 6. Okay. Well, look, this looks a lot like the probability of event E or event F. So my event E here is flip heads, and my event F is roll a 6. Okay. So whenever you see the or statement, okay, what mathematical operator is it always? What is it always going to be? It's going to be this and then sometimes what? So what is it always? Addition. Yep. So it's going to be, you take the probability of the first event and add to it the probability of the second event. So it's probability of flip heads plus the probability of roll a 6. And then you have to subtract sometimes the probability that E and F happen. So I'm going to write that here. It's the probability of flip heads and roll a 6. All right, well, remember, looking back, I'm going to come back to this slide real quick. Remember, the correct answer to this problem is 7/12. Okay, so when we do this formula, we better get 7/12. Okay? So don't overthink this, okay? When you flip a coin, what's the probability you get heads when you flip a fair coin? Thanks, Melissa. I appreciate it. Yep, it's 1/2. Plus, what's the probability you roll a 6 on a 6-sided die? Yep. Now, here's the thing. What is the probability you flip heads and roll a 6? Okay, so these events are not disjoint. You can do this at the same time. You can flip heads and then roll a 6 on a coin. Like, you can do this together. So look back in your notes. What did we say the probability of this was? Probably flip heads. There you go. Look, Melissa, thank you. I appreciate the help in the chat, Melissa. Yeah, look. Probability of flip heads and roll a 6, 1/12. That's what we did yesterday. Tuesday. Sorry, all my days feel the same. So minus 1/12. So look, I'm just going to rewrite it down here now, just so it's a little bit easier. You have 1/2 plus 1/6 minus 1/12. So you're going to need a common denominator to add all these up. So the least common denominator here is actually 12. So 1/2 is going to become 6/12. 1/6 is going to become 2/12. Minus 1/12. Well, check this out. 6 plus 2 is 8. Minus 1 is exactly what we thought we would get, the 7/12. So this formula works, okay? So I'm going to put a little cheers here. The formula works. Woo! So listen, you're always going to add, okay? And it never hurts to write the subtraction part out. And then sometimes what will happen is the subtraction will just be 0, okay? So how about I do an example where we have to like think, are the events disjoint or not disjoint? Okay, does that sound, so maybe one that's a little bit harder, but I think maybe more fun. Does anybody need to copy before I go to the next slide? Okay. Here's the next problem. Okay. And the next one is about drawing cards from a standard deck of cards? Okay. All right, so I just want to go through this, okay? Does anyone in here, just out of curiosity, not know what's in a standard deck of cards? It's okay if you don't. It's not a big deal. How about this question? How many cards are in a standard deck of cards? Okay, 52. Yep. Okay, 52 cards in a standard deck. So let's go through what's in a standard deck of cards. Okay. How many suits are there in a standard deck of cards? There's 4 suits. Yep. What are the red suits? We got diamonds and what else? Diamonds and hearts. Yeah. It's the suits I think about with my wife. No? Okay. Yeah. What are the black suits then? So we got the red suits, and then what are the black suits? Yep, clubs and spades. I'm gonna put spades and clubs. Okay, so there's 4 suits, right? There's the diamonds, the hearts. Oh my God, the spades. Looks terrible, but. And then the clubs. My club looks like a person there. Sorry, but you get it. All right, and then within each suit are the same cards. Okay, they all have the same following cards. They have the cards 2, 3, 4, 5, 6, 7, 8, 9, and a 10. And then they all have a jack, a queen, a king, and what else? And an ace. Yep, they all have that. Okay, so there's 13 cards in each suit. Okay, there's 13 diamonds, 13 hearts, 13 spades, 13 clubs. And then there's 4 of every card. Okay, there's 4 jacks, there's 4 tens, there's 4 nines. Okay, all of that. All right, so now that we've had a good kind of just quick introduction to what's in a deck of cards, here's what we're going to do. If you select or draw one card at random from a deck, okay, so you're just going to shuffle up the deck of cards and you're going to just draw one card at random. Okay, what is? So I have 2 probability questions for this. Is everybody okay if I go to the next slide? Anybody need to copy still what's in a deck of cards? Everybody good? You know, I'll put on my mic. I'll put on my video just to make you laugh for a second. Can everybody see my video here? If you ever look I don't turn my video on too often, but you guys see what's in my background here? You guys see, what do you guys know that I'm a fan of, if you can see here? It's Star Wars, right? Like that's Yoda. Oh, you can't see. That's Yoda. That's an X-Wing. That's Qui-Gon. But so for the holidays, I got 2 decks of cards from family members. I got a Star Wars deck of cards, and I got a Mandalorian deck of cards. So I don't know why. I just thought of this example. That's funny. Okay. All right. So we're gonna draw one card at random. Okay. Here's the first question. What's the probability the card is a queen or king? Okay, it's a queen or a king. I have the same deck. That's good. So it's a probability of queen or a king. Okay, so again, I know sometimes I repeat myself, but When you see the or statement, what does that imply? What mathematical operator? Addition. You're going to add. Okay. So you're going to add and sometimes subtract. So it's the probability you draw a queen plus the probability you draw a king. But let's write down minus the probability that the card you draw is both a queen and a king. All right, well, how many queens are in a deck of cards? How many total cards?
52.
Yep, so what's probability you would draw a queen? Yep, you got it. Thank you, Melissa. It's 4 out of 52. What's the probability that it's a king? Well, how many kings are there?
4.
Yep, 4 out of 52. Now ask yourself this. Can you draw a card from a standard deck and have it be both a queen and a king? No. So what do you think that probability is?
0 over 52.
Yeah, 0 out of 52. Yep. So look, this is 4 plus 4 gets me 8 out of 52, which we can leave as 8 out of 52. That's totally fine. It would also reduce to 2 out of 13 if you wanted to reduce the fraction. Or 8 divided by 52 gets you 0.154 when I round it to 3 decimal places. Okay. Now let's try this one. All right. What's the probability the card is a queen or spade? Queen or spade?
They're still down here.
I'm sorry? Was that a question or just if you forgot you had your mic on? Okay, we'll just say sounds like I've got the mic on. All right, so queen. You're good. You're good. That's okay. Usually I have a crying child in the background, so I wouldn't worry about it, you know. So it's probability of a queen. And when you see the or statement, what mathematical operator? Addition. Yep. Plus the probability of a spade. And then look, I'm going to write the probability that it's a queen and a spade. Okay. We know the probability to get a queen is 4 out of 52. What's the probability you get a spade, though? How many spades are there? Yep. So this is 13 out of
52.
Okay. Now watch. Listen. If you were to just add here, you'd go 4 plus 13 gets you 17. If I were to say the answer is 17 out of 52, I would get the problem wrong. Okay. Does anybody know why I would get it wrong?
Because it's supposed to find a common factor.
Well, hold on. Melissa, there's a queen of spades, right? So what would happen is here, I'm counting the 4 queens, including the queen of spades. When I count the spades, there's 13 spades, including the queen of spades. So I have double counted the queen of spades. So really what this subtraction part does is get rid of that double count. So what is the probability? Can you draw a card from a deck of cards and have it be both a queen and a spade? Yes. Yeah. And it's the queen of spades, and there's 1 queen and spade in the deck. So minus 1 out of 52. So here's an example, right, where the first one where they were disjoint, but then the second problem was they weren't disjoint. So 4 plus 13 is 17 minus 1. 16 out of 52 would be the right answer. Okay. This would reduce to 4 out of 13. Which gets me 0.308 when I round it. Okay, so for this one here, you just have to follow the formula, right? Like, you know, just follow the formula, and then as you go through it, think if they're disjoint or if they're not disjoint. Okay. All right, what do you think? Not too bad? Not the worst?
Yeah, not too bad.
Okay, so I understand. Probably could be a little confusing. Yep, Alexandra, I hear you. I know. Trust me, I know. All right. Let's move on to another type of rule, and I think these problems are more fun. These next ones here. Okay. So before we get into the next rule, we're going to talk about is the general multiplication rule here. I have to talk about types of events and how events interact. Okay. So when you have two events, or it can be even more than two events. Okay. Events can be either what we call independent events or dependent events. So independent events or dependent events. Okay, two events are independent if the occurrence of the first event E does not affect the occurrence of the second event F. Okay. Let me give you an example of what I mean by independent events. Things like coin flips and die rolls are independent event. Like if I say I want to find the probability that you flip heads and roll a 6. If I flip heads, okay, so that's my first event E. If I flip heads, will that impact or change the occurrence that I then roll a 6 on my die? Like, does flipping a coin have anything to do with, yeah, no, it doesn't. Or like if you flip a coin 2 times in a row, if you flip heads on the first coin, is that going to change the occurrence that you would flip heads on the second time you flip the coin? Yeah, no. Yeah, so those are independent events. Sampling or selecting with replacement. So suppose you're going to draw a card from the 2 cards from a deck of cards, one after the other. But after you draw the first card, you're going to put it back in the deck and then draw the second card. So this would be like if I wanted to find the probability you draw 2 queens from the deck of cards, but you replace the first queen. You replace the first card after you select it. So like you shuffle up a deck of cards. The probability you select a queen the first time is 4 out of 52. If you put the card back in the deck, what's the probability that you would select another queen?
Another 4 over 52.
4 out of 52, yeah. So it doesn't change. Like you getting a queen the first time doesn't impact the probability you get a queen the second time if you put the card back. And then the third way things can be independence is selecting from a large population. All right, so what I mean by this is suppose you're going to select 2 people at random from everybody in the United States, literally everybody in the United States. And you want to find the probability that you get two males in a row. If you select a male the first time and remove him from the population of the United States, is it going to change to any measurable number the probability you would select another male if you just removed one from the population?
No.
Yeah, no. So when you have a large population, even if you take people away or things out of it, it doesn't matter. They will still be independent. Okay, so now the next thing is dependent events. So 2 events are, sorry, a little bit of a typo. Dependent, if the occurrence of the first event does affect the occurrence of the second event F. And this generally happens here this way. When you select without replacement. So let's go back to that deck of cards example. Suppose you're going to draw 2 cards from a deck of cards, okay? And after you select the first card, you're not going to put it back in the deck, okay? So you shuffle up your deck of cards. You want to get 2 queens in a row, all right? The probability you get a queen, the first card is 4 out of 52, okay? So imagine oh, sweet, my first card I selected was a queen. I'm going to put it over here to the side. Now, what's the probability then that I go back into the deck and get another queen if I removed a queen already? Yeah, 3 out of 51. Yeah, because there's 3 queens left. Yeah. And there's only 51 cards left, right? Because I took a queen out. So that's an example of dependent events, okay? Also here, kind of very similar here. It's selecting from a small population. So what we're going to focus on today is this stuff. All right, and next class, we're going to get to dependent events, okay? All right, this next formula and these next type of problems are actually my favorite type of problems to work, okay? So is everybody okay if I go to the next slide? All right, well, I'm going. We'll push on. Okay. So this rule I have here today, rule number 3, is the general multiplication rule for independent events. So this rule works when you have the 2 events are independent. Okay, so they meet this criteria here. And the rule goes like this. For any 2 independent events, okay, we'll call those events E and F. All right, we have the following. If I say, hey, what is the probability that event E and event F happens? So event E and F happens. Well, just like before, and I'm going to go back real quick. Whenever you see the or statement, you're going to think addition. Whenever you see the and statement, you're going to think multiplication.
Professor, I'm sorry to interrupt, but if we have the O, we still need the minus after the plus.
Yes, it depends if their events are disjoint or not. That's the hard thing. Like you have to figure out if they're disjoint or not.
Thank you.
Yep. So whenever you see the and statement, it's probability of E. You figure out what the probability of the first event is, and then all you're going to do is multiply it by the probability of the second event, F. That's it. Okay. So like, does this work?
Easier than the first one.
Wait a second. Actually, these problems can get a little bit harder. Trust me.
Okay.
They're also more fun. There are more fun. But let me rephrase that. The problems seem a little bit more difficult initially, but once you figure out how to tackle them, like the approach to it, maybe they are a little bit easier. All right, so I want to go back to you flip a coin. And then roll a die. Okay. And the question we did first was, what's the probability you flip heads and you roll a 6? Okay, probably you flip heads and then you roll a 6. So we've already done this, right? What is the correct answer? Does anybody remember what the correct answer to this is? Right here. Yeah, it's 1/12. Probably you flip heads and roll a 6. The correct answer is 1/12. Like you should get 1/12 when you do this. All right, so let's see if the formula works. Okay. So the first thing here, when you see the and statement, like right here, The and statement, right here, and. What mathematical operator does that imply? Did I say that implies?
Multiplication.
Multiplication. So the first thing you have to ask yourself is the event E, flip heads, and the event F, roll a 6, independent? And the answer is yes, right? Like if you flip heads, it has no bearing on if you roll a 6. So it's the probability of flip heads times the probability of roll a 6. Well, when you flip heads, what's the probability you flip heads? Yep. And then on a 6-sided die, what's the probability you roll is 6? Yep. Check this out. Multiply fractions, you just multiply across. 1 times 1 is 1. And then look, 2 times 6, 12. You got it. So this formula works. Okay, it works. Maybe it is. Maybe it seems easier, right? Initially than the general addition rule. Yeah. You guys agree? Maybe this seems a little bit easier.
It seems for now.
Okay.
Oh, yeah, I agree.
Okay. But let me tell you this. Actually, this coin flip, one coin flip and one die roll is actually too easy. We're actually not going to. This type of stuff is too easy. So let's make it harder. Okay. We can expand on this. Okay. So is everybody okay if I go to the next slide? So for independent events, E, F, G, H, how many ever? Not just 2. It could be 4, it could be 6, it could be 1,000. Okay, doesn't matter. So for independent events, E, F, G, H, how many ever there are? We have the following. If I ask you to find the probability of event E and event F and event G and H and doesn't matter how many, okay? As long as they are independent, okay? When you see the and statement, what does it imply? What mathematics? Multiply. So you're just going to take the probability of the first event, E, and you're going to multiply it by the probability of the second event, F, times G, times H, so on. How many ever there are, you would just multiply them all together. Okay? That's it. That's how you tackle this. All right. These problems tend to be a little bit more interesting. All right. And so what I want to do is I have 4 examples of this stuff picked out. So before we take our break, I want to do 2 simple examples. And then during the second half of class, I'll do what I think are more interesting examples. Okay. So give me 10 minutes to get through, 10, 15 minutes to get through the boring stuff. And then when we come back, we'll do more interesting stuff. Okay. Everybody okay if I go to the next slide? Okay. So here's the first example. Suppose you flip a coin 6 times in a row. Okay, imagine you're just going to take a fair coin, you're going to flip it 6 times in a row. Okay. What's the probability you flip heads 6 times? Okay. Does this seem a little bit different than the ones we've been doing, maybe a little bit harder? Maybe not. I don't know. Okay, so you're going to flip a coin 6 times in a row. And I just want to figure out the probability I get heads 6 times in a row.
The spacing will be too much.
Say that again?
The spaces will be too much.
The spaces will be too much? What do you mean by that?
How do you call it? The total number of occurrences.
It's not too bad. It's actually not too bad. Let me ask you this. Does anybody have a guess to what the answer is? I'm just curious. No guesses? Okay. So look, how you tackle these harder problems, the key for these really difficult problems like this one is how you write it. And what I mean by how you write it is like what you write as the probability statement, okay? So all we know how to write things is with ands and ors, okay? So look, probability you flip head 6 times. So you're going to need to flip head 6 times in a row. Jeez. Okay. Excuse me. I need to get some water. Okay, so if I'm going to flip head 6 times in a row. The first flip I'm going to put is head. Okay. What if I want to flip head 6 times in a row? What does the second flip need to be? What do you think? Also head. Yeah. What does the third flip need to be? Yep. You can see the pattern. And then the fourth is a head. Fifth is a head. And then finally the sixth flip is a head. So look, notice how I kept a space between them. If I want them all to be heads, all of them to be heads, okay? Does the first flip or the second flip need to be heads, or is it the first flip and the second flip needs to be heads? So logically, if I want them all, am I going to put an and or an or here?
And.
Yeah. So the first and the second needs to be a head, and the third, and the fourth, and the fifth, and the sixth. They all need to be heads. Okay. So now look how I wrote it. All right. When you see the and statement, what does the and statement imply to do?
Multiply.
Multiply. You just need to ask yourself if they're independent events. And the answer is yes, right? Like if I flip heads the first time, it's not going to change the probability I flip heads again. Okay. It's not. So this is just the probability. The first is heads times the probability the second is heads times, and I'm just going to keep going, the probability the sixth flip is heads. Well, what's probably you flip heads the first time? Yep. What's probably you flip heads the second time? Same thing. Yep. And the probably flip heads the third times is 1/2. And the fourth time is 1/2. And the fifth time is 1/2. And the sixth time. So it's literally 1/2 times itself 6 times. Okay. Or 1/2 to the 6th power. Well, look, 1 times 1 times 1 times 1 times 1 times 1 is 1. 2 times 2 is 4, 8, 16, 32, 64. So the probability, if you were to flip a coin 6 times, okay, and you get heads 6 times in a row, you'd only do it 1 in every 64 times you did this. So it's a small probability, okay, low, but non-zero, you know. And look, would you guys agree that like the hardest part is really just figuring out how to write it? Like after you figure out, oh yeah, you just could do it with the and statements. This one didn't seem as bad.
I was thinking of the tree. How you call it?
You don't you only need to do the tree if I ask you to find the sample space. And this one I'm not going to ask you to find. The sample space is too large here to find.
Oh, yeah, that's why I say it's gonna be big number.
Yes,
The space will be too big. Okay, so but usually you said that's also not for big numbers too, right?
that is correct.
Okay, thank you.
Like on your homework that's coming up, I ask you to find the sample space once, and it's a very manageable number to find the sample space. All right, let's do. All right, before we take our break, I'm gonna do one last example. And it's gonna be a dice example, so I'm sorry, okay? And it's this game called Yahtzee. Has anybody ever heard of Yahtzee? This game? Never get. I'll show you why you never get Yahtzee. Okay. So Yahtzee is this game where you roll 5 dice. Okay. So that's just the game. Okay. The game of Yahtzee, you roll 5 die. You roll 5 dice. Okay. And you look at your results. So now here's the thing. I've actually forgotten how to play the game of Yahtzee, but Melissa kind of got to it here. You say you never get Yahtzee. In the game of Yahtzee, when you make this roll on your dice, you get to yell, you get to go Yahtzee, and you win that round. Okay. Melissa, what's getting a Yahtzee? Do you know?
It's when you get the same number, I think 5 times.
Yep. It's when you roll the dice and all the numbers come up the same. Okay. All right. So here's the question. You roll 5 dice. What's the probability all 5 dice come up with the number 1? All right, so what that means, I'm going to take in my hand and I'm going to roll 5 dice, and this is what comes up. They all land and they stop rolling. And that's what I got. And then I get to yell, Yahtzee, Yahtzee, and I won. I'm getting a little too excited for yelling Yahtzee. Okay. So, I don't know. How would you even solve this problem? I have no idea. You roll 5 dice, was probably all 5 dice come up with the number 1. I don't know. Let me ask you guys this question in the chat. Do you think, yes, that's it. Does it seem like you would tackle it just like this problem here, but instead of the first is a flip is a head, it would be the first die is a 1, the second die is a 1, and so on? Does that kind of make sense why you would tackle it this way? And that's why in the chat, it does end up being 1/6 to the 5th power. Yeah. But look, let me show you this, okay? So it's a probability all 5 dice come up with the number 1. Okay, so you roll this dice and they all come up with the number 1. So you just have to figure out like a creative way to do this. So it's the probability the first die is a 1. And the second die comes up as a 1. And the third die is a 1. And the fourth die is a 1. And the fifth die is a 1. All right. So this gets a little bit weird, but like, would you guys say that when you roll dice, they're really kind of independent of each other? Like if a 1 comes up on the first die, it doesn't really change the probability a 1 would come up on the second die. Yeah, I think they're independent. A lot of people say, well, you know, if you're rolling them together and they bump into each other, the only problem with that is you're not technically wrong. It's just there's no way to account for how much influence it is. So we assume that, look, yeah, the dice are independent of each other. You know, the odds are not going to change if you get a 1 on the first die. So then I know I sound like a broken record here, but the and statement implies what again? Multiply. Yep. So it's probably the first die is a 1. Times probably the second die is a 1. Times the third die is a 1. Times the fourth die is a 1. Times probably the fifth die is a 1. And I know it's been in the chat, but you know, what's probably a roll of 1? It's 1 out of 6.
Not a 6.
Yep. So this is 1/6 times 1/6 times 1/6 times 1/6 times 1/6. So 1 times 1 times 1 times 1 times 1 is 1. And 6 to the 5th power. Thanks. Yeah, is 7776. So the probability that you roll, yeah, well, the probability that you would roll 5 dice and they all come up with the number 1 would be 1 in 7,776. So it's not very often, okay? I wouldn't spend your day trying to do it. If you do it, you got lucky, really is what's going on, okay? All right, I do just want to do one follow-up question to this. Let me know if does anybody need me to stick around on this slide before I go on? Okay. All right. So in the game of Yahtzee, getting a Yahtzee is that all the dice match, right? Okay. So again, the follow-up question to this is, if you roll 5 die, or 5 dice, what's the probability all the numbers match? Okay, so that's a Yahtzee. Okay, it doesn't matter. They don't all just have to be 1s, okay? So you get a Yahtzee if all the numbers match. So what are the ways that they can match? They can all be 1s. What else could they be? All the dice could come up. Yep. It could all be 2s. They could all be 3s, all be 4s, all be 5s, or all be 6s. So it's the probability that all numbers match. Okay, so that's the probability you roll all 1s. Roll all 2s. Roll all 3s. Roll all 4s. Roll all 5s. Roll all 6s. So now you have to ask yourself here, what goes in here? Is it and or ors?
And
Well, so can you,
Oh,
so we got 2 different things here, right? And or ors, okay. So can you roll the 5 dice and have them come up and be all 1s and all 2s at the same time?
no.
No.
So what would it be then?
and oh,
Or.
Or, yeah, I want all 1s or all 2s or all 3s or all 4s or 5s or 6s. So now the next thing you have to ask yourself here, when you see the or statement, what does it imply? Addition, right?
So,
Now you have to ask yourself this. When I say sometimes subtraction, you only have to do the subtraction if it can happen at the same time. Okay. So can you roll 5 dice and have them all be ones and all be twos at the same time?
No.
No, right. So it's disjoint. So that cannot happen at the same time. So I don't mean to go back really fastly, but really fast. But look, that means the probability that they would all happen is 0. So you don't need the subtraction here. That's why you just need to do the addition because we all realize, look, they're disjoint. It won't happen. So we figured out the probability you roll all ones in the previous example here. It was 1 in 7,776. What do you think the probability you roll all twos is? You think it's the same exact thing?
yes.
Yep. Yep. So you would add this together 6 times. So this would just be 6 and 7,776, which I think reduces to 1,296. Yeah. So the probability in the game of Yahtzee that you actually get a Yahtzee, it'll happen only in one time in every 1,296 rolls. Okay, that's the probability. So that's why you've probably never gotten a Yahtzee. You probably have never rolled the dice almost 1,300 times, you know? So
Wait,
that's
Professor.
yeah.
I'm sorry. I have another question. Let me see. Can you just explain really quickly one more time why you don't use the subtraction at the end since it's or?
Yeah, so you only have to do subtraction. Good question. You only have to do subtraction if the events can happen at the same time. So like, look here, there's no way if you roll 5 dice, they all can show up as a 1 and at the same time all show up as a 2. Right? Like I can't roll 5 dice and be like, hey, look, they're all 2s and all 3s. Like you can't, right? Because you can have only all 1s or all 2s or all 3s. Like you don't need the subtraction here because the events cannot happen at the same time. That's why. So that's just why I left it off.
Okay, thank you.
Yeah, no problem. All right, so when we come back from our break, let's take a little bit of a break. We're going to do some more interesting examples, okay? So let's start back at 1:05 p.m., okay? So we'll take a 7-minute break, all right? 6-minute break. So I'll see you guys in 6 minutes, and then we'll do some more interesting examples.
2:05.
2:05. Sorry, I don't even know what time it is. Thank you. All right, everybody. Ready to finish up for the afternoon? Still with me?
Yes.
Okay. So I have what I think are two interesting examples for the second half of class that are a little bit harder. Okay. So this first one here, let me put a little context behind it. This is about a blood test called the ELISA test. I'm just curious, does anybody know what that stands for? It's an acronym for something. I used to know it. I kind of forgot it off the top of my head. But so what this is a specific blood test that's given to people, and what it's designed for is it's designed to test for any foreign pathogen in your blood system. And so one of the common uses for it is to test for, there's a bunch of different blood pathogens in it, but one of the common tests is to test for HIV, okay? So it's commonly used to test blood for HIV. And now this is an incredibly common test, okay? For example, the last time I got my physical, this is pre-COVID. I think I got a physical. I can't even remember now. Okay, but I go get my yearly physical. And has anybody ever gotten like blood work done when they've gotten a physical? Yeah, like it's just common. Okay, like when I got my last physical done, they did this test on my blood. Like it was just, that's how common it is. Okay. And what the drug claim, or what the test claims is that it is 99.5% effective at identifying, I'm going to put FP, a foreign pathogen, in blood. Okay, any foreign pathogen, it's 99.5% effective. Okay. So what that means is if you take the test, the probability the test comes back correct is 0.995. Okay, is that a pretty good test? That high probability? What do you guys think? If something is 99.5% effective, that pretty good?
Yeah.
Yeah, it's totally good. It's really good. Okay. Now the probability of the test is incorrect then, and I'll explain what that means, is just 1 minus this, so it's 0.005. Okay. Incorrect in the terms of this test is what they call a false positive. It's really hard to actually know what the real value of a false negative is. Okay. But what's a false positive?
They say it's positive, but it's not.
Okay. Yeah. So let's, for the context of this problem, let's just pick HIV. Okay. So a false positive would be somebody takes the test and the test comes back and says the individual has tested positive for HIV, when in reality they do not have HIV. Okay. Is that a good or bad result?
Bad result.
That's a really bad result, right? Very scary, very bad result. All right, so I've got a couple questions for this, okay? All right, everybody okay? Gotten the numbers written down? Everybody good? So just remember, 0.995 is the probability it's correct. 0.005 is probability it's incorrect. Okay. So here's the first question. If 10 people take the test, what's the probability it comes back? What is the probability all, sorry, I got a little sidetracked there in my mind. If 10 people take the test, what's the probability all 10 tests come back correct? Okay, so just 10 random people are going to show up. You know, they don't even have to be in the same hospital or doctor's office. Okay. 10 people are just going to show up and take this test. And we want to find the probability that all 10 tests are correct. I don't know. How would you handle this one? So let me ask you this. What did I say that the key to solving this correctly is? It's how you do what? Starts with go on ahead.
How we put them?
Yeah,
How we arrange the question?
How we arrange them?
how you write it. That's what
How
I'm
we
getting at.
write it, yeah.
Yeah, you guys are right. Okay. So you can kind of see how this is going. So the probability, I want all 10 correct, is equal to, what does the first test have to be? Yep. And what does the second test have to be? Yep. And you would keep doing this. And then I do some dots to let me know the pattern continues, and all the way to the 10th test. Okay. So the next thing you have to ask yourself is, okay, I see the and statement, it implies multiplication. Are these independent? So like what I mean by that is just think about this. Like when I got my physical done over a year ago, okay, and my blood work came back, is that going to have any bearing on if some random person in some other location, is it going to affect the probability that their blood test comes back correct or incorrect? No. So yeah, so it's all independent. So it's probably the first is correct. Times, and you would keep going. The 10th is correct. Well, what did we say the probability that they were correct was? Yeah, and it would basically be times itself how many times?
10 times.
Yeah, so it's 0.995 to the 10th power. So grab your trusty calculator. Okay. So to do this in your calculator, you're going to go 0.995. And then does everybody see where my mouse is? Swirling around the screen. You guys can. Do you see this little caret button right here? This little hat button looks like a little up sign. If you click that, that'll take you to the exponent power. If you have a TI-83, it just shows the caret, and then just type in 10. And then how many people got this number? So Bertha got it. Okay, yep, thanks. So look, the probability that if 10 people take this test, all 10 would come back correct is 0.9511. Still pretty good odds, right? 95% chance that it would happen. Yeah, it's pretty good odds. Okay. All right. Does this problem, at least this one right here, does it still seem kind of like the other ones? Not too bad?
Yes.
Okay. All right. Let me ask you a much harder question now. Okay. Everybody okay if I go to the next slide? Okay. How many people today, literally today in this country, do you think are going to have this blood test done? There's no right or wrong answer. What do you think? Is it a lot or a little people are going to have this blood test done today, literally today?
A lot of people.
A lot of people, right? You know what? Like even people who just go donate blood, right? If someone's going to go donate blood, they're going to run your blood through this test, okay? No matter what. Even if you're like, no, I'm fine. They still run it through this test. You know, I got it done the last time I had just general blood tests done for my physical. Every time you go to the hospital and, you know, people going for surgery, when they take blood pre-surgery, they're going to run the blood through this test. So there's a ton of people. Okay. I'm going to lowball it. Okay. Do you think at least 1,000 people across the entire United States are going to have this test done today? Yeah. It's going to be way more than 1,000, but let's just say 1,000. Okay. If 1,000 tests are done, okay, what's the probability at least one test comes back incorrect? Okay, so at least one of the 1,000 tests is going to come back incorrect. Okay. So I'm just trying to. Oh my God. So this test, okay, is literally used. I was just reading about it on my phone now. It's used for like a ton of different stuff. Okay. Geez, a lot. They might even use it now for COVID testing, even a little bit. Okay. All right. So 1,000 people are going to take the test. Okay. What's probably at least one test comes back incorrect. So what is it? What does it mean to be incorrect again? It's a false what?
Positive.
Yeah. Okay. So basically, let's keep it with the HIV example because that's the most common use for it. That means what's probably at least one person today is going to take the test and they're going to say, "Hey, you have HIV," when in reality they do not have HIV. Okay, that's a scary outcome, right? I have no idea how to do this problem. Does any? I kid around. I know how to do this problem, but can anybody guess what the key word or words are here that make this a little difficult?
At least.
At least one, right? The words "at least one" make this a really difficult problem. Okay, so this is probability at least one incorrect. Yeesh. Okay. I don't know. All right, so you had to pay attention. This was yesterday. I said, "Hey, look, I'm going to ask you a problem that's really hard, and there's going to be this rule that seems super easy. This super easy rule that is going to really help us later on." Does anybody remember what the first rule we learned was? Started with a C, if that helps. Yeah, complement rule. So look, whenever you see the problem with the keywords, this at least one. All right, you're going to want to use the complement rule. So now here's the tricky part. What is the complement, the opposite of at least one being incorrect? This is the hardest part of this problem. What is the complement to at least one incorrect?
Everything is correct.
Say that louder, you have it right.
Everything is correct.
The complement to at least one incorrect is that everything is correct. So look, let me just explain that, okay? So this is, yep, that is correct, Melissa, yeah. So look, If 1,000 people take the test, you could have 0 come back incorrect. You could have 1 come back incorrect. You could have 2 tests in the 1,000 come back incorrect. You could have 3, you could have 4. And what would be the worst case scenario? That 1,000 people take the test.
Everyone comes negative, false positive.
Yeah. So at least 1 incorrect is literally all of these. Everything from 1 to 1,000. Okay. So the complement's what's left over. Okay. So it'd be 1 minus the probability of 0 incorrects. Well, that's 1 minus the probability. 0 incorrect is the same thing as they're all correct. So this is 1 minus. If you want to find the probability that 1,000 tests come back all correct, the first is correct. And the second is correct. And you would keep going all the way into the 1,000th test is correct. Okay, that's good. When you see the and statement, what does that imply?
Multiplication.
Yep. Are these independent events? Like is my test or the one other person's test? Are they all independent basically?
Yes.
Yeah. Yeah. Even if they're the same hospital, they're independent. Like what would conflate things in the hospital is if there was a problem in the lab, not with somebody's blood, you know? So this would just be 1 minus, probably the first is correct, times, you'd keep going, the 1,000th is correct. Well, this is 1 minus, probably they're correct is 0.995. And so how many tests do I have here? I have 1,000. So it'd be 0.995 raised to what power?
1,000.
Yep. So grab your trusty calculator, okay? So 0.995 raised to the 1,000th power is 0.007 when I round it. Okay. So this is equal to 1 minus 0.007. So the answer to today, the probability that at least one person's test comes back as a false positive is 0.993. Okay, so that's over a 99% chance that someone's test comes back with a false positive today. So is somebody's test, basically what I'm saying here, is it like almost 100% sure that somebody's test today, literally today, somebody who takes the test today is going to get a false positive?
Professor, I have a question.
Yeah, yes.
How did you get the 0.993?
If you take 1 minus this, so if you go in your calculator, 1 minus 0.007.
Okay, sorry.
That's okay. That's all good. So look, this is what's today. Someone is going to get told that they have a foreign pathogen in their blood system like HIV, when in reality they don't. Okay, it is literally going to happen today. Okay, so let me ask you this: what do you think happens when somebody's test comes back positive, where for a test like this? What? The answer is not panic initially. What do you think medical professionals do? So let me ask this, the medical professional, another test. Yeah, that's the thing. They do another test and another test and another test and another test. Okay. Because look, in the aggregate, okay, even something that's 99.5% effective, okay, if 1,000 people, if enough people take the test, it's going to fail eventually, you know? It's only going to work 99.5% of the time. So just is anybody surprised by this result that today someone's going to get a false positive? Got to probably be multiple false positives today. I think it's a little crazy, right? When you see something like this. No? Nobody found this interesting? Okay, I found it interesting. All right, well, let me ask you this. Was at least the math behind it not too bad? I mean, I'm going to do another one of these, but.
The maths are still okay for now.
All right. So let me do one more problem, okay? Another one of these at least problems, okay? Everybody okay if I go to the next slide? Pretty good. All right. The last, well, this might be our last problem. It depends how long it takes. I want to do a problem that's about the Challenger disaster. How many people know what that is when I say it? There's actually
Battleship.
Say it louder.
Is it a battleship?
It's not a battleship. There's actually a Netflix documentary about this. All right, Melissa, what is it? You can turn your mic on. What is the Challenger disaster?
It was like a space shuttle that exploded midair on television.
Yeah, so in 1986, I'm just going to give a little history behind this because this is an incredibly interesting problem to me. In 1986, we were at like the height of the space shuttle program. We don't have the space shuttle anymore, right? And so what made this specific one interesting is NASA was like, okay, we need to get more people jazzed about space. So what they got an elementary school teacher to train with the astronauts and then was going to go to the space station. And they were broadcasting this to schools live on TV because it was such a big deal. Oh, we're sending a teacher into space. We're going to do, grade school from space. It's going to be great. But then on live TV, what a lot of people believe happened is the space shuttle exploded, but that's not exactly what happened. I'm going to talk about what exactly happened. And it was a national tragedy. It was really, really sad. So just out of curiosity, now that I say that, I know it was a long, long time ago, but from history classes, does this ring a bell to more people now? Hopefully. Well, regardless, if you look on Netflix under documentary sections, there's a whole documentary about this. So you should, if you got an hour and a half to kill later for a little bit more history, you can figure that out. But what I want to do is I want to relate this to our class and probability. Okay. I want to compute the probability of what NASA calls a shuttle loss. So we're going to compute a probability they literally told the astronauts before they shot them into space. Okay. And so what shuttle loss is, that's kind of a way of saying the shuttle just doesn't return home. So there's a disaster like the Challenger disaster, and the shuttle is a loss. And when the shuttle is a loss, the astronauts are not going to make it home. Okay. So to do that, I have to give you some information. Okay. In every item on the space shuttle gets what's called a criticality rating. Okay, and the criticality ratings are like this: 1, criticality 1, criticality 2, criticality 3, criticality 4, so on, okay? The most important items on the space shuttle are what are classified as criticality 1 items, okay? Okay, these are the most important. And let me give you some information about criticality 1 items, okay? The first piece of information about them is they must work 99.99% of the time. Okay, they won't classify, they won't let you put this item on there unless the engineers say, look, there's a 99.99% chance that this is going to work. The other things that have to happen is there's no backup to this system. All right, so there's only one of these items. If this item fails, there's no item to replace it. So let me give you an example of a criticality 1 item. Okay, the wings on the plane. Okay, those are classified as criticality 1 items. Like if the wings fall off, are there another set of wings to just slap on the plane and everything is okay? No, like that's okay, Michael, but glad you're back. Yeah, there's no like extra wings. A few other things that are like criticality 1 items, like I think the landing gear was, and a few some other items I can't even remember off the top of my head. And the other thing is they must all criticality 1 items must work independently of each other. What that means is like the system that monitors the wings doesn't monitor the landing gear. Indeed, the most important thing about criticality 1 items is if a criticality 1 item fails, there will be shuttle loss. Okay. So let me ask you this. Do you want a lot or a little criticality 1 items on the space shuttle? You want a little. You want as few as you can have, okay? You know, I don't want to go fly into space with a bunch of systems that have no backup, and if they fail, the shuttle's going to be a loss, okay? I don't want that. So just pick a number. Okay, somebody pick a number. How many criticality 1 items do you think there were on the Space Shuttle Challenger? Okay, 77. Any other guesses? I only got Melissa, who's been active, 77 guesses.
5.
How many?
5.
I think 5. Okay. Anybody got another guess? I'll take one more. Neither of them got it right. I'm not saying that their numbers were not close. I'm just saying neither of them got it right. Not 77, not 5. Kat says 2000. All right. On Challenger, there were 748. Okay. Criticality 1 items. Okay. Does that seem like a lot to you, to anybody who's still paying attention? Yeah.
Oh yeah.
Yeah. It seems like a lot to me.
Not so much.
Yeah. So what happened was a criticality 1 item did fail in the Space Shuttle Challenger. It was an exterior fuel line. And if I'm remembering my history, forgive me if I misquote, but I think an exterior fuel line failed and like liquid nitrogen engulfed the space shuttle, and it actually engulfed in a flame. That's really what happened, and it's just sad from there. Like you can watch a video on YouTube and see what happened, but so it didn't actually blow up; it just got engulfed in flames. Okay. So let's find the probability then. Look. That even before the shuttle took off, that it would be a shuttle loss. Okay. So there's 748 of these. They work 99.99% of the time. Okay. So just so we're clear, what that means is the probability it works is 0.9999. Okay. All right. Everybody okay if I go to the next slide? hope so. I'm gonna go. Okay. So what we want to find is the probability of a shuttle loss. Okay. What's the probability that these astronauts, even before they lit the fuel to shoot them into space, what was the probability that they weren't going to make it home? Okay. So now my question for you is, what does it take for there to be a shuttle loss? What needs to fail? So let me go back. What is all that it takes for the thing to fail? Melissa said it. All it takes is one. Okay. All it takes is one of these criticality 1 items to fail and the shuttle's a loss. Okay. But let me ask you this. If 2 criticality 1 items fail, are they a loss? Yep. If 3, if 4, if 5, if 6, if 7. So all it takes is at least 1 is what I'm getting at. So the probability of a shuttle loss is the probability at least 1 criticality 1 item fails. That's all it takes, is just at least 1. Okay. Well, what's the key word in there that tells me how to solve this? Or what is the key words in here from like a previous problem?
At least one.
At least 1. So I'm going to need to use what rule here?
Complement rule.
Complement.
Yeah. So this is 1 minus the probability of the complement. So what is the complement of at least 1? Going back, the complement rule of at least 1. See where my mouse is?
0.
0.
We're all wrong. Yeah, 0.
Okay, so 0 items fail. Okay, so if 0 of them are going to fail, what are they all going to do?
They all work.
They all work. Yep. So this is 1 minus probably the first item works. And the second item works. All the way up to and what one works? The 748th works. Okay. So now the next thing you have to ask yourself is they have to be independent of each other. But if you look here, it says right here in C, all items must work independently of each other. Okay. So then I see the and statement. It implies multiplication. So this would be 1 minus the probability the item works is 0.9999. So it would be 0.9999 raised to what power? Yeah.
748.
So let's grab that trusty calculator. So the probability I'll work is 0. I'm just going to round it to just to make the math easy. I'm going to round it to 2 decimal places. It's 0.93. So even before the shuttle took off, this is what we were saying. There was a 7% chance that they weren't going to make it home. Okay. Does that seem high to you? Would you let me ask you this, would you get on an airplane if they said, hey, there's a 7% chance you're not going to land?
That's too high.
It's way too high. It's way too high. I wouldn't do it. I'd take the train. Okay. I ain't doing it. Maybe I'm not going to go to Florida ever again. I don't know, but anyways, it's just interesting, right? Like do you think they obviously told the astronauts this before they launched them into space? They would. Yeah, they absolutely did. Absolutely. Everybody knew what the risks were, and that, I just think it's quite interesting that like they know that this is the risk and they still took it, it's just interesting. So I hope you enjoyed, even though the last two examples were a little like depressing, maybe. I don't know. I actually didn't watch a documentary. With my son at home, I don't have time to do anything fun anymore. That was a bad joke, but not unnecessarily true. So I haven't had a chance to watch it. I hope people don't judge me too harshly on that comment. I love them. Thank you. All right, I'm going to stop the recording.